All right, hello students. Once again, welcome to Oceans Robotics. And in this video, we are going to be covering elastic properties of solids / Hooke's law, and of course, Young modulus. As usual, feel free to pause the video intermittently. Of course, I will still be covering every point captured in the notes in the course of this introduction. So let's get started. Preview the formulas. Very important. Hints, tips, definition of terms. Okay, so what is elasticity? What is elasticity? You can as well call it elastic deformation, elasticity, or elastic deformation. All right, they are the same thing. Now, what is elasticity or elastic deformation? It is the ability of a solid to regain its original shape, okay, and size upon the removal of the applied force or the force which tends to distort it. So that is elasticity. Now, this is a property that is inbuilt in every solid, not just in a few elastic materials around us. Like many students quickly think of rubber bands, they think of springs, they think of extensible ropes and strings. No, every solid possesses this property, and we are going to see that in the course of this introduction. Okay, so Robert Hooke, all right, in 1660 studied this elastic property of solids, and then he gave his law, Hooke's law, known as Hooke's law. All right, now the first version of Hooke's law, let me start here. Hooke's law. Hooke's law. Okay, first version states that provided the elastic limit is not exceeded. Of course, this law is captured in the note. Please rewind the video and go through the note. Hooke's law states that provided the elastic limit is not exceeded, all right, the applied force is proportional to the extension. Okay, that's the first version of Hooke's law. And of course, if we remove this sign of proportionality, we introduce constant, which is K, and K is known as the force constant, or elastic constant, or the stiffness of this, in the case spring, okay, stiffness of the solid body or material. All right, and the unit of K, of course, K is force, if we make it the subject, force over extension, and if force is in Newton and extension in meters, therefore K, the unit of K is Newton per meter. All right, remember that K, yes, K is proportional to force. That means if K goes up, all right, if the value of K increases, therefore means that the force required to distort the body will also go up. The two of them are directly proportional. Okay, and of course K is inversely proportional to E. That means if the value of K increases, the extension gotten will be very small. All right. Now let's take the second version of Hooke's law. The second version of Hooke's law, again, Hooke's law, the second version states that stress is proportional to strain, provided that the elastic limit is not exceeded. Okay, so as usual, if you remove the sign of proportionality, we introduce a constant. In this case, this constant will be our Young modulus or elastic modulus. Some textbooks use E. Then we have strain like this. So elastic modulus or Young modulus, is equal to, that's the ratio of stress to strain. Okay, so, and if stress is force over area, okay, whereas strain is the extension all over the original length. Please take note of this. Now the unit of stress is Pascal, PA. All right, of course, that's Newton per meter square. It shares the same unit with pressure. I hope you've not forgotten that. Okay, whereas strain is unitless. Strain is unitless. Don't mind the grammar. Okay, that means it does not have units. The unit of extension is meters, and the unit of course, the original length is meters. So the two of them cancel out. Now, the Young modulus will be stress over strain. So F over A divided by E over L naught. All right, and if you tidy this up, you will get that Young modulus is equal to F LO all over AE. So I trust that you should be able to tidy this up so that we don't waste time. Okay, now we can see that Young modulus is directly proportional to the force and of course the length, but inversely proportional to the area or the diameter or the thickness of the solid material, and of course extension. Now I'd like you to see that since stress has its unit as Pascal and strain does not have any unit, therefore the unit of Young modulus is what? Is Pascal, or you can still say Newton per meter squared. So Young modulus shares the same unit with stress and of course pressure. All right, remember again that there's a link between Young modulus and force constant. Now take a look at this. F is equal to KE, and from the formula of Young modulus, we saw that Young modulus is equal to F L naught all over AE. Okay, now if we make F the subject of the formula, we are going to get that F is equal to that's over 1, you cross multiply. F will be equal to Young modulus times A times E all over L naught, like this. Okay, where E is the extension, L naught is the original length, A is the area, and of course this Young modulus. Now, can you see a resemblance between this and this? Okay, let me rewrite this and then ask you to spot the similarity that exists between the two of them. So F is equal to KE, and then F from the formula of Young modulus is equal to Young modulus times A all over L naught, then times E. Okay, so we can see that F here, E here, E here. Therefore, we can conclude that K is equal to Young modulus times the area all over length. Okay, so we can see that the force constant, or the stiffness of the solid material, is directly proportional to the Young modulus, and the diameter, all right, or the area of cross section of the body, and then inversely proportional to the original length. Please take note of the again, don't forget the units of K. All right, K, its unit is Newton per meter. All right, it shares the same unit with surface tension. Remember, surface tension is also Newton per meters. Surface tension, that's the force that acts on a unit area on a straight line, an imaginary straight line drawn right on the surface of a liquid that is at rest. That's surface tension. So K shares the same unit. Just like in physics we have quantities that share the same unit with other quantities. Of course, when you say work done, for instance, work done, the unit of work done is what? That's force times distance, Newton meter. And of course, moment. Do you remember moment? Moment of a force also has the same unit as work done. That's Newton meter. The difference is that this one is force times distance, but this is force times perpendicular distance. Okay. All right. So Young modulus, just like Young modulus, shares the same unit with pressure, or you can say stress. That's Pascal. Okay. Or Newton per meter squared. Again, let's take note of the difference between stress and strain. All right, so let's talk about the difference between stress and of course strain. Okay, it can be tensile or compressive. I think we are going to consider that after this segment. Now, stress is a measure of the extent of distortion in the body. This one is the extent of a measure of the extent of deformation in the body. All right, this one begs the question, to what extent does the force affect the shape of the body? To what extent does the force affect the size, or you say the length of the body? Of course, remember that this one has its unit as Pascal, that's Newton per meter squared, whereas this one is unitless. It does not have any unit. Okay, I think that's all I can say here. Now, tensile or compressive. We also have a third one, shear, but we don't normally consider this for O levels. Okay, now if I have this body like this, and this force and this force tends to pull this body apart, that's tensile force. okay, which will eventually bring about tensile stress or strain. Okay, now if the forces are in this direction, they tend to squeeze the body to bring about distortion. Then this one is compressive, okay, load or force or stress or strain. Then you talk in terms of stress or strain. Then we have a third one, shear. I have this body like this, and then the force acts like this, trying to change this plane shape to another shape. Let's say square to rhombus, okay, or rectangle to parallelogram. Then this one is shear force or load. In this case, you'll be talking about shear stress or strain, not tensile or compressive. Okay, finally, I want to talk about the plot of F against E. All right, and it looks like this. You have F in Newton plotted against E in meters. Okay, if the graph starts from the origin, you get a straight line like this, provided that the elastic limit is not exceeded. Now, two questions can come on this. Number one is the slope of this plot F against E will be what? So the slope, we know slope is rise, okay, over run. That's the vertical all over the horizontal. So change in the vertical axis, which is force, all over change in the horizontal, which is the extension. And we can recognize this from F is equal to KE. If we make K the subject of the formula, K is equal to F over E. So that means that the slope is also K. So this is the slope or the gradient. We use M often to represent the slope. So don't forget that. Now they can as well ask us of the area, okay, under this graph. Okay, so let's take a look at, I'm going to withdraw this graph. So I have E meters, I have F in Newton, and of course this from the origin. Now if the question says the area under the plot or the graph of F against E is equal to dash, okay, just produce this down to the horizontal axis, and then you have discovered that the plane shape we have here is a right angle triangle. So the area of this plane shape is what? Is half, you remember, half times the length times half breadth times the height, if you want. This is the height of the plane shape, which is F, okay, times, okay, the base, which is E. So can you recognize this? This is what? The work done, or you can say the elastic potential energy stored in an elastic material or in a spring, whatever. So the area under the graph or the plot of F against E is equal to the work done, okay, or the potential energy stored in the spring. All right. Okay, so finally, let's explain this popular graph that several questions usually come out from. Again, I have my F and I have my E. Now this graph looks like this, and then like this, and what's going on? Oh, okay, so something like this. Something like this. Oh God. Okay. So I believe you've got the picture. My pen tablet is giving me trouble, but it's okay. So let me use another color and see this point. Okay, this point. I don't know if this color is visible. Then this point and this point. Okay, so let me call this A, B, C, D, and E. Okay, now AB, line AB, that's the proportionality region. Proportionality region. Okay, and then AC is the elastic region. Okay, that's the elastic region. And then B is the proportionality limit. B itself, that point is the proportionality limit. And C is the elastic limit. Okay, I think I will complete this here. Elastic limit. And then D is the yield point. At this point, the elastic material will have yielded all its elastic properties and would have literally become a plastic yield point. And then E is the fracture or breaking point. So that's all. Please take note of this. Let's now go over to section 2 and then begin to answer questions. Thanks for watching. Okay, at Oceans Robotics, we have a team of godly, competent, and reliable teachers to coach and mentor your children with respect to math, physics, and chemistry, and as regards different aspects of coding or programming. So we look forward to hearing from you. Bye-bye.